It's recording now. So that's the and number 4. What's the vibration? So that's the topics to be covered. And so basically, the level you will see is similar to the first exam, and the problems will be very similar to your homework problems. So hopefully we will just revise some of the homework problems to make sure you learn the topics through doing the homeworks there.
Excel problems?
No, you are not required to use Excel to do any calculations. You
don't have to?
No.
No.
That's exam number 2. And we have project 2. Project 2 has already been uploaded last week.
You've made 2 of us cry already.
So project 2 basically that's very related to the topic to be covered tonight. And project 2 would be much easier than the project 1. Actually, project 2 is the compilation of 2 homework problems from your textbook. Since you have already developed your Excel for numerical integration for dynamic analysis, you should be able to do the project very quickly. As long as you, especially after the discussion of tonight, you will see how you can handle the project 2 very easily. So just to make sure you get some practice on the forced vibration of MDOF systems. So no homework tonight.
Thank you.
Basically, we will not have any homework problems anymore. So project 2 will cover the topics for the forced vibration as well as free vibration of MDOF systems. That's the plan. So project 2 is due. Number 2.
Some sort of.
So you will have almost 17 days, a little bit more than 2 weeks to finish that. Actually, yeah, if you check your homework problems from chapters 11 and 12, you will see actually that project 2 is a combination of 2 homework problems from your textbook.
We didn't do chapters 11 and 12.
We did 9 and 10. Yeah, we didn't do chapters.
Yeah, we will do that tonight.
2 chapters.
Very young. We're very stressed about that.
Okay.
Like last night in Professor Fiocolo's class, what we talked about was your project. Yes, this is what Anthony, Michelle, and I talked about. Like he was talking, we would whisper to each other like, okay, what do you think?
Okay, anyway, let's start the discussion of the topics for tonight.
All right.
Because so far, we have already covered all the topics for SDOF systems, and we have already covered the free vibration of MDOF systems, such as given the stiffness matrix, given the mass matrix, we should be able to calculate the natural frequencies and the mode shifts for MDOF systems there. But how about the response of the MDOF systems under earthquakes or under other types of dynamic load? For example, if you have a two-story building and under earthquakes, how can we calculate the responses of each floor of the two-story building? So that's the topic of tonight. That's because I believe that's a natural extension of what we have learned, because we know how to calculate the response of a single degree of freedom system under earthquakes by numerical integration. And from your project one, you have had a very extensive practice in that part. But tonight we will focus on how to calculate the responses of the MDOF systems. So that's about the forced vibration of MDOF systems. So here are the objectives for tonight. Actually, these two topics are in your chapter 12 textbook, chapters 12 and 11. Very ambitious plans for tonight. Trying to cover 2 chapters in one class.
Another week if you need. But we still have more homework.
Okay.
Jesus, Mary and Oprah.
So, so the first topic here is to stop forced vibration of MDOF systems. And if there are any dynamic load, how can we the second one is need formulate the damping matrix. How damping ratios measured. So this is different from the SDOF system. Regarding damping, if we have multiple degrees of freedoms, how can we consider damping? Actually, that's the most challenging part for structural dynamics. That's the goals for tonight. Actually, 2 topics. So now let's talk about the equations of motion for MDOF system, MDOF damped system. The general equation for MDOF damped systems. I believe everyone's very familiar with that. This is very similar to the SDOF systems. The only difference is we use matrix instead of single value variables here. The mass matrix and the displacement times the acceleration vector plus so we have the mass And the mass times the acceleration plus the empty times the velocity plus the stiffness times the displacement equal to the force. So pretty much that's very similar to the SDOF system. The only difference is that we use matrix and vectors. Because for different mass, we have different displacements. So how can we solve this problem? We have to assume a solution for any. Actually, this is a system of differential equations. For example, if you have a two-story building, you need to solve two differential equations. If you have a skyscraper, 100 stories, you have to solve a system of equations with 100 differential equations.
I guess you should use a computer for that.
Yes, we can use, we use a computer for that, but we need to know what is going on behind the black box, especially some fundamental understanding that help us to avoid some mistakes when you do analysis here. So we can assume a solution in this way if we want to solve that theoretically. Assume. Very similar as what we did for SDOF system. You can assume that displacement vector is equal to sigma I. So the total displacement of all the degrees of freedom can be expressed as the summation or the combination of n's mode shift times the displacement of one mode.
Mass variable is that y sub I?
That's y sub I and t. So for example, we know if we have the degrees of freedom equal to n, there will be n. The total number of mode shifts will be equal to n, right? So that we should be able to have total number of vector equal to n vectors equal to n. And for corresponding to each mode shift, we have the time-dependent response of the system equal to y sub it. We assume that. So and we can also written that in terms of matrix so that we can have terms of matrix and vectors. Where the modal shift matrix is equal to P1. Where the YP is equal to we can further express the term in the middle in terms of in the form of matrix. We use a not big matrix to include all the modal shifts, and we use a vector to include the response for each mode. Does this make sense? And if you still remember how you dealt with vectors and matrix in your linear algebra, so basically the radix forming the equivalent of the middle term. Do you agree with me? Any questions? Yes?
So, y of t, are those, what you said, those are time dependent
Yes.
solutions?
Yes, they are time dependent. They are all the y sub 1 through y sub n over all of them are time dependent. They are functions of time. Because the force here is time dependent. The PT, the top equation, PT is time dependent. So that which we will have a component of the response is time dependent, while the modal shifts they are time independent. So modal shifts phi1 through phi n they are time independent. As we have already done last time, those are only functions of the stiffness matrix and the mass matrix. The modal shifts they are time independent, while those are time dependent because the force is time dependent. With force varies, here the responses should vary this time. Does that answer your question?
Is y then is the force, or it's just like values that represent the time part of the solution?
So y just the number to represent the component that varies with time. Okay. So this is not the force. These modal shifts.
Is there a formula or anything for it?
Yes, we should be able to calculate the modal shifts as we did last time, right? So given the stiffness matrix and the mass matrix, which firstly we can calculate the natural frequencies, and if we have already calculated actually the phase are the eigen vectors for the mass matrix and the stiffness matrix, what we did last time. So any questions, online students? Are you guys agree with me with this transformation between vectors and matrices here? This is not that very fancy linear, just fundamental linear algebra. So that means we can, because we have already expressed the displacement as the modal shift matrix times the time-dependent variable. We should be able to derive the velocity and the accelerations. Right? So that means the velocity vectors should be equal to velocity should be equal to the modal shift matrix times t. Because the modal shift matrix is time independent, so when we calculate the derivatives, this state, well, the only derivative we need to do is regarding the y, regarding y here. And similarly, velocity can be expressed, the acceleration can also be expressed as the modal shift times the second derivative of the y here. Nothing fancy, right? Because the modal shift is time independent. So now we should be able to have a new form for the equation of motion. We have the M times E. Let's call this equation 1. So we have a new form for the equation of motion. So actually, this all the above is convert the equation of motion is actually to separate the response to two parts. One part is time independent, the other part is time dependent. So for a system of differential equations, that's the typical method. I'm not sure how many of you have already taken advanced mathematics about the solutions of system of differential equations. This is one of the most popular way to solve the system of differential equations. So, any questions up to here? Yes, Anthony?
Is that why?
Oh, dot.
Yeah.
Oh, dot. Yeah, the first one should be double dot.
That's squared?
Why dot?
No, I know, but above the bracket.
No, that's a flourish.
The curly bracket.
Oh,
It's
above
just
the,
a
yeah,
flourish.
got it.
Oh, here?
Yeah,
Oh,
I got
that's-
it.
Oh, okay, that's not the square, that's just the right side of the bracket.
Thank you.
So remember that the P, that's the combination of all modal shapes. So now we multiply the transpose of the P on both sides. Multiply. Equation 1. That we have the P times M. And this will be the most beautiful part of dynamic analysis. So that we got a new equation. We multiply the transpose of the phi on both sides. Make sense? No fancy transformation. We just multiply a new matrix on both sides, and this is equal to transpose of the phi.
Why is M and C in brackets but K is not?
Oh, it should be bracket. All of this three will be matrices. Very good catch. Thank you, Anthony. So actually, if we look at this form, actually this form can be reduced to very interesting matrix. So, any questions up to here? As I mentioned, no fancy, just some basic fundamental linear algebra here. So now, remember the also clarity of model shapes. You remember? Solution. For the clarity of model shapes, because we should have the transpose of phi times n, and there will be a diagonal. So actually, the product of the three matrix will be a new matrix with only diagonal elements. That means we will only have numbers in the diagonal line, So all the other elements will be equal to 0. So why? Because we know that the A, we have the R and M, A n equal to 0. R not equal to. For two different model shapes with two different modes, the model shape of R times the mass matrix times the model shape of phi will be equal to 0, so that we will have only diagonal elements for the new matrix here. Yes. Similarly, we will have P diagonal. Stiffness, we have a new diagonal stiffness matrix. So this matrix will have only numbers in the diagonal line. All the other elements of the matrix will be equal to 0. This is very important. But how about the damping matrix?
Are those K's or U's?
Which one? K? Yeah, that's K. Sorry.
That's okay.
And that's a K. That's a stiffness. For the damping, we can only assume because we don't know what is the damping matrix. Actually, theoretically, we cannot derive the damping matrix, unfortunately. So that we can only assume. P is also and we assume that then the phi is also go to the damping matrix. Phi. Damping matrix. So then we have stars. Start, mass, surface, and then damping matrix fits here. Actually, this procedure is called decoupling of MDOF systems. So with this procedure, the MDOF system can be decoupled to multiple SDOF systems. So you will see why. You will see why. This is called decoupling. Equations. Reason why is because the new matrices uh, the new mass matrix will have only diagonal elements. All the other elements in the matrix go to zero, equal to zero. And similarly, the K is also diagonal one. By multiply the transpose of the node shape matrix, we can decouple the equations of motion to several decoupled of equations. So by this one, we will have by M R Y T and then equations of motion has already been converted to new mass matrix damping P and stiffness matrices are in the new force. And so all of them are star. Any questions up to here? So this would be very helpful, very helpful. So these equations of motion now are written in the form of matrices. And if we write the equations of motion in the not in the matrices, we write it in the system of equations, we will get the new loop for all the equations. So decoupling. Motion. So we will have if we express the equations of motion in the regular way, we will have the M1 star. So now we will not have a matrix here. We express that in terms of the element times Y1 star. The total number of equations we have here is we have the total number of decoupled equations equal to. So any questions up to here? So initially, the stiffness matrix and the mass matrix and the active matrix, the different model shape, they are coupled, but now we have the decoupled equation. Actually, each decoupled equation corresponds to a single degree of freedom. This is corresponds to a single degree of freedom. M1, that's a calculated value. That's a calculated value. C1 star and K1 star, both of them calculated value. And the P1 star can also be calculated. So the only way for us to do is to solve for Y1 through Yn through Yn. So here for Mi, this is a single degree of freedom. Freedom system. And we can multiply, we can divide that by m. Right here is called eyes. Photo, then preview. So now we have a SDOF system. We have already discussed the solutions for this system. The solutions will be the solutions for that is we have the this is the solution that we discussed before for a damped system. So the first is the transient response, and this is the steady state.
Omega D is the damped natural frequency.
Yes, omega di, that's a highest damped natural frequency. So where the and that's equal to Ai star over mi star. Omega di, that's equal to omega I. So actually, by decoupling, we have already reduced so the solutions of multiple differential equations to a set of solutions for multiple single degree of freedom systems. And the initial conditions can be expressed as example, the y. This is the initial displacement. Velocity. should be able to solve solve that. And the total. After we solve that, we should be able to find the total displacement. Is equal to the that's how we calculate the response of the MDOF system. The first thing we decouple the different modes, and then we combine the response of different modes. And we better to demonstrate the example. This is a theoretic background. So if we have an example here, how we can solve the responses. So any questions so far? Actually, the solutions of the MDOF systems is very similar to the solution of SDOF system. The only thing you need to do is, firstly, you need to calculate the modal shifts, and then you use the modal shifts to decouple the system, so that all you need to do is to solve multiple single degree of freedom systems. That's what you need to do for your project to actually. So if you follow this procedure, you should be good shape for your project. You figure out the mass matrix, stiffness matrix, and you assume a damping matrix here, so that you can solve the system under earthquake using numerical. And since there will be convolution integral over there, so you can use numerical integration that you have already developed in your Excel to find out the responses. So now let's see what will happen for an example here. Any questions so far? Okay. So after example, you will see actually this approach is very powerful.
Do back to the previous page for like 1 second. Thank you.
Welcome. So any other questions? Yeah. So now let's see what will happen if we have an example here. So this example is actually the same structure that we used. Actually, this example is a homework example in the chapter 12.6. We have a cantilever beam. And two masses here. Four, and then this is the is a cantilever beam. Two methods, right? One is a free end, the other one is the middle of the beam. And if this system is under a force, this force is if we apply a force, that's a constant force. Right? If we apply a force on the free end of the cantilever beam, up very suddenly in a very short time, actually, we know that the cantilever will vibrate initially, and then it will keep as a constant deflection. So now we need to determine the response. Know that $29,000 KSI. It's a steel beam. Moment of inertia is given. Then and the mass matrix is also given. Stiffness matrix. So this is a typical problem with MDOF and by constant mode. Design parameters are known to us, and what will be the response of the beam? And the two methods, and the location of the two methods there. So that's the So now let's have a short break, and after the short break, we will resume the discussion of the example. Show you how we can calculate the responses of the two methods and using the procedure of decoupling. Any questions from my students?
It's good. Calm down.
Let's do this.
That one area, like monuments. The
So online students, can you hear me? Can you still hear me?
Yes, I hear you.
Oh, thank you, Jim.
The one is
So now we are given all the
the big difference.
structural properties of this system here. So it's a 2 degree of freedom system here. So in order to calculate the responses of the two methods here, we need to know the modal shifts, right? Know the modal shifts firstly. So that's why why we need to do the eigenvalue analysis first. Eigenvalue analysis. So there are two options. Option one, you may do that hand calculations because you have only 2 degrees of freedom. Hand calculation will be doable, feasible in this case. Another option is to use MATLAB directly. So I don't know what is your preference, but tonight I'm going to show you how to use the hand calculations firstly, and then later on I'll show you how to use the MATLAB. Now let's solution, and firstly we need to do eigen analysis here and to figure out the model shapes. Actually, the model shapes are given last time. We spent spend some time to calculate the natural frequencies as well as the eigenvalues last time. So this time I'm just going to give you those numbers. And as we went over the hand calculations. You guys can hear that. Oh. So the natural frequencies. You can just plug in all the numbers to get the. So based on the natural frequencies, we should be able to get the first model shape. One. The model shapes here, so that the model matrix should be equal to. As the last time we spent quite a while to derive those figures nicely. I'm just gonna give you the model shapes and the natural frequencies directly. So if some of you would prefer to using MATLAB, so there is a way for using MATLAB too. Are you ready for MATLAB? A little bit MATLAB here. For MATLAB, so MATLAB, firstly we need input some variables. We have the n. No? Is given to us for two. This is the male. And female. And we have the E. On the side. Please keep in mind that for the forces, and we will use caves. For the length, we use inches. Make sure you use that. For the 100, this I value, and EIL n times L. So that's all we need here. And now we formulate the mass matrix here. We call the mass matrix. As ML over 4, 0, over 2. That we can. So this is a mass matrix. Just here. You may use any symbol. So that's the mass matrix. So any questions up to here? It's just you input some variables and get as a, and now we use the key. The key we use Steve. In the stiffness matrix, we have that 48 times I over 7 times L cubic times. The first one is 5 minus 5 minus 60. That's based on what we are given. Just click. So that is the stiffness matrix. So that's the numbers for the stiffness matrix. So does this make sense?
Scroll up. You scroll up a little.
Pardon me?
You scroll back up.
Oh, so scroll up.
Yeah.
Just zoom out. Easy. So that's the input. So now we need to do the eigenvalue analysis to find out the natural frequencies as well as the model shifts directly. But I don't know what function should I use in my I assume it is eigen.
Function.
So we just use help. Oh, E. So that's help A. So that's kind of take a look at eigenvalues and eigenvectors. So you might have, right? So now you can look at how to calculate. So there are different types of inputs and outputs. So probably we are interested in the eigenvectors as well as the eigenvalues. So the V is the vectors, D is the eigenvalue. For example, here, VD eigen A produces a diagonal matrix D of eigenvalues and the full matrix V whose columns are the corresponding eigenvectors. So that the AB equal to V times D. But this is not what we want because we have two matrices, one mass and the other. We just look down, see whether we can have this one. Okay. Eigen AB produces a diagonal matrix D of generalized eigenvalues and the full matrix V whose columns are the corresponding eigenvalues, so that A times V equal to B times D times C times C. So what is A, what is B? We need to figure out. Should the mass be the A and the stiffness be the B, or vice versa? Remember, for the MDOF systems, actually the eigenvalues are the omega square. Omega square. So it looks like the right side should be the B should be the mass, because this is the K times the displacement equal to mass and the displacement equal to times the square times the omega square. So that we can just go ahead and copy this down. Remember, the A should be the stiffest. The B should be the mass. Ready? So those are the eigenvalues and the stiffest matrix is the eigenvalues. That's a little bit different from what we have. Actually, let's first take a look at the lateral frequencies here. So actually, please keep in mind that eigenvalues are the square of the lateral frequency. What's the first eigenvalue here? It's 1,000 times 0.1, that's 100. So that's the square of the first eigenvalue. That's the first square of the first natural frequency. If you take the square root of this one, what will you get over here? And how about the second one? Please check. So this should be 22,065. 2,653. Square root. That's a natural frequency. What number did you get? One?
51.51.
Okay, and is this one consistent with the hand calculator one?
Yep.
Okay, very good. But how about the eigenvectors here? Those numbers look so different from what we have, right? But please keep in mind that the model shifts only numbers show the ratios of the displacement for the two masses here. If you divide the matrix by the first number, what we will see over here, for example, I'm gonna divide the vector by the first rows. Oops. And just get the vector. I'm just gonna divide vector and the eight. It's gonna be times anyway, maybe either for you. You just divide divide all the numbers in a matrix. For example, for the first column, you divide both numbers by the first number, so you will have 1 here. Right? So you divide this one by itself and divide this one by 4.4386. What will you get? If you make this one, this should be equal to this number over the first number. Number. What number did you get? 43 something?
Yeah.
Is that consistent with the second number of the model shape? Similarly, you can do that by divide this number by the top number over here. You will get the model shape. That here. The okay, this be equal to inverse. B equal to I just divided. I just make the first rows, both of them equal to 1, so that the second row will be the ratio for the second. So is that those model shapes correspond consistent with what we have. And that's how you can use MATLAB to do the model shape, find the model shape and natural frequencies directly. Any questions up to here? So now, then back to the result here. This is the result given by MATLAB. Please keep in mind that model shapes are only numbers show us the ratios between the risk and the displacement of two matrices. So the numbers that does not make any sense. Only the ratios between the two numbers in the same column give us the information of the model shape. And the eigenvalues on the square of the natural frequencies, other than the natural frequencies themselves. So any questions for the MATLAB part? So in the exam, actually, can use MATLAB.
Can you scroll back down, please?
I explain the numbers we get over here. Sure. So anytime if you are given the stiffness and the mathematics, you should be able to use this function MATLAB to find out the natural frequencies as well as the model shape directly. But so the D as a diagonal matrix shows us the square of the natural frequencies. So the actual natural frequency should be the square root of these two numbers. Please keep in mind the natural frequencies should be the square root of these two numbers. And the model shapes, you can use those numbers as your model shapes because we are only interested in the ratios of the two numbers in the same column here. So either this equal to 1 or to some other numbers doesn't matter. So you can use this one. And when you do analysis, actually, you will see that those numbers doesn't That will not affect your result if you use different numbers. So is that clear?
Yeah, can you scroll down to the code you put on at the bottom to get the eigenvector?
Yeah, this you mean here?
Yeah.
Yeah, so that's the eigenvectors expressed with the first row is equal to 1. So basically, I divided the initial eigenmatrix by the first row, the numbers in the first row, so that we can have the first displacement equal to 1. So this is more like a normalized model shape. This is more like a normalized model shape. And the top one is non-normalized. Either you can use either normalized model shapes or non-normalized model shapes. That will not affect your final results. That will not affect your. So in the exam, either way you will get the correct answer. Yeah.
What did you type in for stiffness at the top?
Here. So this is stiffness matrix is given. It's given in terms of the BI and the mass. So that's based on the structure analysis. And this will be given to you directly because this course will not have you to spend quite a while to figure out the stiffness matrix by using the matrix method or displacement method. Now that will too much work. But in the exam, typically that will be given to you directly.
Stiffness will be given, you say?
Yes, stiffness matrix will be given to you.
That's so kind.
Fire.
Could it be given to us in a MATLAB file?
No. So yes, one goal here is to train you better handle the eigenvalue analysis here and have a better feel about the relation between the natural frequencies model shift and the eigenvalue analysis here. So how the eigenvalue are calculated, that's not the point. That's a linear algebra. So now we should be able to see as a number based on the time calculation. So MATLAB is very powerful, as you have already seen. There are a lot of resources on Google, internet. So if you explore more, you will be surprised on how MATLAB is
Looks like
popularly used in the engineering field, civil engineering, mechanical engineering, acoustic engineering, so a lot of different type of. So now, please keep in mind that that's just the initiation of this problem. We need to figure out the response here. So we have already calculated this is part of the model shape matrix. So now we can find the star matrix, the star matrices, the n star. N star is equal to the transpose times the initial measurement matrix here. And, actually, you can also do this by using MATLAB directly.
it correctly.
Directly. But here I'm just going to show you time calculation firstly. So The transpose should be one. So this is the transpose. Right? Transpose means we make the first row as the first column and the second row the second column. Right? Times the m. The m is L over 4. And this one is and we should be able to get the that's the new mass matrix. And that is the mass matrix star. That's the M star. As you can see here, the M star has numbers in the diagonal line. Right? So the other two are 0. The other two are 0. So does this make sense? So alternatively, you can use MATLAB. Because MATLAB, I have already calculated the V. Right? So we can use the M star mass star is equal to the V is the mass, the model shape matrix. Use prime, the transpose. That's the transpose in times mass itself times the V. Why both of them equal to 0, equal to 1.
Is it because it used the original V matrix, not the one above?
Because we have the yes, this should give us the same answer here. I don't know why. Interesting. Oh, both of them equal to 0. Let's check the V prime here. V prime, that's
Did you do an element multiply instead of a? Did you do a dot and then time? Do an element wise multiplication?
oh, there will be no dot because 4 should be matrix. No, should be matrix. Product of matrix. Double check the y is equal to 1 here. Check the mass matrix here. Mass matrix is not why mass star. That's interesting. Interesting. It's normalized and non-normalized. Did not affect our result here. Now let me try to use the normalized. Probably we need to use the normalized. We use the norm equal to the norm Mass star. Yeah, this makes more sense. Okay. Okay. In this case, that means anytime we need to use the normalized ownership, normalized ownership when we calculate that mass star. So we better use the normalized one. So that means the elements in the first in the motorship matrix should be equal to 1. The first row should be equal to 1, so that we can get the drag n star. Please keep in mind that the model shapes should be normalized. If we use the non-normalized, something will be strange. Something will be strange. So any questions up to here? So if we compare this number, this is the consistent with our hand calculation. So that's why it's very, very important to be able to do hand calculation. Sometimes the software may give you a wrong number.
Why is he looking at me when he says that?
Let me just
He totally was looking at me.
So this is the mass star. This is the mass star. So next step we calculate the K star. K star.
Okay.
Yeah. So I'm just gonna have you to calculate the K star in the MATLAB directly. And if some of you have the laptop, if you do not have a laptop, we can calculate that. Can see how I did that on the screen, right? So now we calculate the stiff star to be equal to nothing. MATLAB is because I can just copy paste. Right? Change this to D. That also is prime. Right?
Yeah. There's a comma.
This is the thickness. Online students, are you with me for the thickness start here?
Yes.
Okay. So pretty easy, correct? If we use MATLAB. If you do not have the MATLAB installed on your laptop, you should be, or your desktop or your Mac book or Mac station. There is a MATLAB cloud that you can use. You should be able to use your school email address to log in or register for a free version for the MATLAB cloud to use that in cloud. So this is the stiffness matrix star. And this is consistent with what I did by hand calculation. So either way, we can also star and can also use hand calculations here. we just substitute everything so that we can. Inch, per inch. So as you can see here, that K star is also a diagonal matrix. The other two is equal to 0, is equal to 0. So any questions up to here? So we have the M star, K star. So next, for this problem, there is no damping. There is no damping. Right? So we just need to calculate the Q star. That's the force. For the force, we also need to convert that to Q star. Q star. Is equal to the times equal to Q star. Interestingly here is that even the force is applied to the first mass here. If we calculate the Q star, that transformed forces to the 5K on both. Any questions up to here?
Is 5 kips given in the problem?
Yeah, 5K is given. So 5K a constant force. So that's the piece of 0. So that's a constant force from time equal to 0 to forever. So that means that we should be able to have the decoupled equation. So we have the y here. Then we can have the we have two equations. Yeah, decoupled. Each equation has only one unknown time function. Unknown time function. Does this make sense? So, do you remember how to solve this differential equation? So this is a single degree of freedom system here. Similarly, this is a single degree of freedom system. Now we should be able to solve them. That's what we covered before the first example. Any questions up to here? Okay, so if there are any questions here, you can just go ahead and solve that. Y1T. You saw that? Should we go to? We assume the initial displacement and the velocity is equal to zero, equal to zero. So that the total displacement should be equal to the eigen vector matrix times the equal to equal to solution responses of the. So if there is no damping at the responses of the, and it will be at two different locations. First one is the free end, second one is the middle. Nice. In the middle. Does this make sense? We can also plot the responses here directly because we know that the y1 and the y2t here, y1 and y2t here. Okay. We can just go ahead and yeah, we can also use method to plot that. We can, for example, we can define the t is equal to 1 to 10 seconds. That's a t. We have the y1 is equal to y1 is equal to 0.936 times 1 minus cosine 30 times t. This is the y1 2 equal to 0.008 times 1 minus sine 51.51 times t. So the total based on the u is equal to the so the normalized eigenvector and E and U. Oh. The responses, and that's the responses. Huh. One, and so the responses of the two methods, one in blue and one in red. So which one is the U1, which one is the U2?
Who's the red one?
U2 is the red one?
Yep.
Yeah. Because U2 is the middle length, U1 is the free end. And for the cantilever beam, anyway, we will have that. That in, and if you compare the responses of this beam with the static deflection, what is the static deflection of that cantilever beam at the free end? So that's P L square over 3 times EI, right? You will see that. So structural analysis, given the cantilever beam, what is, and if you have a force at the free end, what is the deflection at the free end? As a PL square over 3 times EI. We compare that. Let's see what we have here. And so the force is equal to 5 times L over that's 2.9793 inches. Oh, no, should be over 3 times EI, sorry. So the static response will be around 1 inches. What is the dynamic? And much more than that. If you look at the red and the blue curve, so the maximum displacement on the dynamic load is pretty close to 2 inches. So that's double the static response. Does this make sense?
Yep.
So this is the example showing you how to use the procedure to calculate the responses of a MDOF system. So, and you should be able to use the same procedure for your project. The project is a 2 degree of freedom system there. So the mass matrix, you should be able to figure out the mass matrix very quickly. It's given in your textbook, and the stiffness matrix is also given in your textbook. You should be able to find those, or you can just Google, because it's only 2-story building with rigid floor. It's pretty easy for you to figure out the M and the K. And the only thing you need to do is to decouple the system to a system of 2 equations there, and solve the 2 equations using the numerical method, either numerical or central different method there. So that means you use your Excel to calculate the response of the 2 SDOF systems and combine them using the model sheet. Yes.
It looks like there's 3 degrees of freedom.
Oh, 3 degrees. That's pretty much the same.
Yeah.
It looks pretty dead.
Yes. It's really that.
To ask about exactly what one of the parts of the project is asking for. It does say determine the responses C, N, T, and A. Are those like the?
Yeah. Yes, the D, let me take a look at that.
Story shears. they kind of are turning
Yeah,
on.
what else did it do?
Yo, I think that just comes.
Thank you,
I
actually.
said, well, I think that's probably.
And that was awesome. I'm not against it.
I feel like you could see my steps. There is most of them, and one is right here. Yeah.
It's the time of night where we lose our.
So here, maybe share that with the online students too. So online students, we are talking about the project here. So the first one, determine the SDOF system responses, DNT and ANT. So what is DNT? The displacement for each floor. ANT, that's the acceleration. Yes. So basically, the thing you only need to do is decouple the equations of motion to 3 SDOF systems, and you calculate the displacement and accelerations for the 3 DOF systems there. Basically, you only need 3 Excel spreadsheet to calculate the D and A. So that's the first one. Second one, for each natural mode calculator, the function times the Falling response quantities, the roof displacement, storage shears, and the base overturning moment. So for example, if you have the D and A, the roof displacement should be directly based on your numerical model. And the storage shears, what is the storage shear? Storage shear would be the shear force. Which storage, that means if you know the displacement here, the displacement here, the shear would be the relative displacement of this 2 times the shear stiffness of this column. Very, very straightforward.
You said the relative displacement times the shear stiffness.
Yeah, as long as you have after you are done with step 1, you should be able to tell the displacement for this level and this level and that level, right? If you know the displacement of each level, how can you tell the shear in this column?
Are we using both diagrams?
Yeah, those are the 2 different structures. And I require you to compare these 2 different structures. The only difference between the 2 structures is the distribution of the stiffness. You can see here. Right? So this each level has the same rigidity, but this one, the bottom has a higher one, the top has a smaller rigidity. You just need to actually you just do both of them and compare the results in the last and then the item B. Does that make sense? A little bit structural analysis, but very basic structural analysis. Like you know the stiffness here, displacement here, you know displacement here. What is the shear force in that column? Easy, right? Because if the stiffness and you should be able to know the relative displacement of each level, so that shear force is a function of the relative displacement. Because the floor is rigid, So that's part B, and the base overturning moment is also very straightforward. Because the overturning moment, if you is equal to, you have a mass here. This mass will have some inertial force. This mass will have some inertial force. This mass will have some inertial force. All of them will induce some bending moment in the foundation. For example, for structure analysis, if I give you a force here, force here, force here, can you calculate the bending moment in the base? So that's the overturning moment. That's the overturning moment. Just use the force times the moment arm, or times the height of each level. So that's the part B. Part B. Part C, at each instant of time, combine the modal contributions to each of the response quantities to obtain the total response. Determine the peak values of the total response for selected response quantity, followed as a function of time the modal responses and the total response. You just, part C, you just need to combine them. For example, you have this is Y1, Y2, Y3. Combine them, you just use the modal shift matrix times the Y1, Y2, Y3, as we did in the example. Does that make sense? Please read your textbook. Please read your textbook. So by reading your textbook, this project can be done very easily. So this is a project. Any questions, online student? Hermit, what's your question? We're good. Okay. Everybody's good. Please let me know if you have any questions when you start doing this project, and we can discuss about that. Schedule a time individually. So this is a procedure about the, but another important part for MDOF system is the damping matrix. So we know the mass and the stiffness matrices can be derived by structural analysis. But how about the damping? The damping is the most challenging part. Talk about damping. That's the last
Can you
part.
actually go back to the solution for a second? I didn't get to write it down.
Okay, this one? Okay,
Yeah.
sure.
All right, thank you.
So damping matrix. MDOF system. So this is the most challenging part for MDOF system. So similar to the SDOF system, there is no way to analytically derive damping matrix. Experiment is to assess a structure damping. Damping. And that's why, as you remember, when we decouple the equations of motion, we assumed, since there exists no flows matrix, we can safely presume C as that the C is also a diagonal matrix. And because it is very impossible for us to do analysis, like structural analysis, to find out the stiffness matrix or the mass matrix, we can only assume a empty matrix for safety. And there are several types. So the first type is we assume C. We can assume that this empty matrix is proportional to the mass matrix. So that the alpha, actually alpha can be find out by experiment. The alpha can be expressed as the damping ratio for each model times the natural frequency. So we can assume theta 1 equal to 5%. For example, we can assume that damping ratio for the first model equal to 5%. We can solve there, after there. So if we assume this equal to 5%, so that we can have a value for alpha for any given structure, omega I, omega 1 can be calculated. This is the first method. Also, we can assume C is okay. Such that the C to alpha 1 and K. So that we can have the alpha 1 is equal to similarly, we assume theta 1 is equal to 5%. So for alpha 1. That's the second assumption. Either the damping matrix, so proportional to the K or proportional to the A. So naturally, there will be the third one. Assume. So the third one is called the relay damping, and that's one of the most widely used. Damping. C is equal to alpha 0 and plus 1. So for example, in future, if you are required to do time history analysis for MDOF systems, you typically need to define the damping. So the most widely used damping is called relay damping. So that you need to figure out the numbers, the values for alpha 0 and alpha 1. So in order to calculate that, we need to know two modes. relay damping. So in future, if you do a dynamic analysis for multiple story of building, don't be surprised by what the hell is the relay damping. That is a relay damping. Relay damping. So based on some calculation, you should be able to the equation you have half times I the J one equal to I 0 I J. So for so typically for relay damping, we need to use two damping ratios. For example, you can pick the first mode theta 1 or the third mode theta 3 and then use that equation to solve alpha 0 and alpha 1. So some softwares may require you to input the number for alpha 0 and alpha 1, or some software needs you to input the damping ratio or the selected mode. So you need to tell this software which mode to use. For example, you can tell this sub 2000 to use first mode or the third mode, and then use input the damping ratios for the. So some some of you may be interested in what damping ratios should we use for different structures. So here are some information. A good engineering judgment. Engineering judgment is the magic. Oh, magic tool.
Signing any. You shouldn't, yeah, put that much steel, that much. Euro?
Okay. Okay, some good engineering. Judgment. So for welded steel, may use the damping ratio 2 to 3%. And for RC, reinforced concrete with cracking, 5%. Without cracking, use 2%. And the wood. So with cracking, the damping ratio is higher. Why? Because yeah, very good. Steel yield, and if there is cracking, the friction between the cracked surfaces will contribute to the damping. For wood, would you expect a higher damping for wood or smaller?
Higher,
It would.
yeah,
Nice.
that's what I meant.
6 to 7% for wood. Bolted steel. For bolted steel and the welded steel, which one will be higher, the damping ratio? Bolted and welded.
The connections are less rigid.
So for bolted, you use 5%. Because welded is yeah, more rigid and the bolts and some tolerance there. So the movement between the bolts and the plates can contribute to the damping here. So that's the damping ratios you may use in future if you are required to do any seismic analysis. I think that concludes the end of the structure dynamics for the semester. And, it's been a very fantastic teaching this course, as well as see the progress all of you have already made for the past few months. Especially, I'm very impressed with some of your work in your project. You did a lot of good job programming, producing the response spectral. Very good job, and looking forward to see you work in the final as well as the project too. Let me know if you have any questions, and enjoy the rest of your evening. And congratulations to Sheila, Hunter, Barrington, and Tony, Nick,
Yeah, congrats, guys.
and Hisham, I believe, Perry.
You left behind, but.
It's okay. Well, you're doing great. Leslie and Phoenix, congratulations. See you around, and let me know if you have any questions.
Thank you, Professor. If no one has question, would you mind you stay online? I just would like to discuss a few things with you, please.
Sure. Yeah, let's stay online for 3 weeks. Okay. I will stop the recording anyway, and